Hello everyone. Today we will talk about a bit more detail about closed loop system and stability. So we had studied so far stability from Bebo point of view or the bounded input bounded output point of view, and also stability in terms of equilibrium point, and then we characterize those as the location of poles of my open loop or a closed loop system depending on wherever you are. So what we will do today is to look a little more detail about feedbacks. So feedback really helps all the time, or there are some drawbacks. We will skip the drawbacks part and we will, do not go too much into the details. And then we will just see feedback help us in a lot of way, and also define something called as relative stability. Okay, so open loop systems are heavily prone to disturbances, right? So the output is affected by change in parameters. System parameters could be like, I'm talking about mechanical system, a mass could change or any other thing change in the system. It could also be changed because of external environmental conditions like temperature, sometimes disturbances act into the system, and I wouldn't know how to bring my system back to original state. For example, if I'm driving a car, okay, and my paddle is at constant position, if I hit a ramp, or an unslope, that is disturbance, right? So if I keep the same paddle position, I keep going through the ramp, I will not be able to maintain the desired speed, and after a while I might even lose the speed and I might just go to zero speed, right? So there is no automation correction if I set my paddle speed to its open value, and just doesn't change it when the disturbance come, right? So this is a block diagram for open loop control system where my disturbances affect my output. Okay, in closed loop system, the output is actually measured and compared with reference signals, which generate an error signal, which I update my control law, and through control law I adjust my actuator, which gives the actual control input to the system, right? So typical thing that could happen are, you have the effect of disturbance, you also have measurement noise, right? So my measuring device may not be very accurate, and they might come into a bit of noisy, and so how do we deal with those, or with these things, the disturbance signals and the measure noise? So we want to keep or design our controller or keep in mind such that I reject disturbances, and I also should reject the measurement noise. Okay, start with an example, right? So this is a model for automatic control of speed for an automobile on a straight run. So I have a reference input, reference speed, I have measured speed, and then this generate an error signal which will decide the position of my throttle, and then this is my throttle, and there could be disturbances in terms of road slope, and it could either be a positive slope or a negative slope. No disturbance could just mean no slope. And this is very simple model of my car. So the car, which you look very big with lots of components, actually looks very small here, right? So it's just first order differential equation or a system with just one pole, and I just get the desired speed, right? So this is like a standard measuring device, like a tachometer in all, and this will convert into an appropriate speed. engine for simplicity is modeled as first order system with time constant of 20s and gain of k, which is typically a value of 1.5 here. The input of throttle angle measured in degree and the output is desired speed, right? And the speed feedback is obtained by tachometer, right? Somewhere in feedback loop, as we have seen in diagram. So this is used to obtain the error signal for changing the throttle angle, right? Or for desired purpose. So we say that throttle angle has a time constant much less than the system time constant, and therefore we could ignore it, right? And it's just modeled as a small gain of k1. So the error k1 gives me the control input, and some typical value we could assume in this case is 50. So just see the diagram for that. It will give me the control input. Okay, the disturbance signals appear on the automobile run up or a down slope, right? It is expressed in terms of percentage of road slope, and I have a 90%, 90 degree could actually means that you're actually hitting a wall and all you just going vertically downward upward. So this signal is converted into equivalent throttle angle, and then you have this kg which take care of the units, and then you have this kg in 100 degree percentage per unit percentage of the slope. So why we are doing this? So let's see in the diagram. So why we are doing this? So if what happen if just do not measure this guy? Okay, I have a reference, I just have an output, right? Suppose there is no feedback, and also take the case of feedback. So what will happen in both the cases, open as well as closed loop system? So we will see that. So given the first condition of first problem, let my reference, or not my reference, okay, the desired speed is 60 km per hour. Okay, and that is in terms of picture, that could be vs is 60 km, or you can say vt from my diagram. And then we have to find r, or the reference signal, with the system being first open loop and then closed loop. Okay, and we will also see how the steady state error for step input changes, right? So let's say in open loop system, so it's steady state, my speed is 60. So this is my open loop transfer function, this is open loop transfer function, this is input, this is my output. Okay. And in open loop steady state speed is 60, and how will my transfer function look like? It's like this. It is k1 k tau s plus 1 and rs. Okay, so this will be my step signal, right? So I have to determine the size of step, I have to determine the size of step here. Okay, so let me just call it some number, say r by s. I will clear. So I am just representing it with r by s because I have to find out the step signal. So I will do the final value theorem, and then I just get 60 is equals to k1 k r, right? So k1, as we have seen in last slide, k1 is having value of 50, k is 1.5. By putting the value I can get the value of r. Okay, and r is 0.8 km per hour. Now let us see the what is steady state error. So if I look at Laplacian domain, ESS steady state error is rs minus ys. Okay, so what we want to compare the error, rs minus ys. So ys here, whatever the y here is the velocity. Okay, so I'm just putting the value over here. I'm taking rs common. Okay, so error just become ess. I do the final value theorem. Okay, so it will be again s into ess. I will put it, s will get cancelled out because my r is r by s. R value I have, it is 0.8. Okay, from here, so I will just calculate this limit and then I will calculate it is minus 74. Okay, now let's do the closed loop case. So in closed loop, reference is still 60. My steady state value is 60. My transfer function will look like this. It's a feedback system, negative feedback system. Okay, so I will again do the final value theorem and then its s will get cancelled. So my r value is 60.8 kilometer per hour. Okay, so now again the steady state error, I will do again rs minus ys. I am putting the value of ys, then I am again calculating final value theorem. So I will get the value of 1 by 76. So this is significantly smaller here, right? So I have a big steady state error. If you will say it's a big steady state error over here and fairly smaller steady state error over here. So you see how the feedback of closed loop reduce the steady state error. Now in next case, let's do some transient analysis, right? So earlier we have done the steady state analysis. So we want to find out at what time the vehicle reaches 90% of its steady state value for open as well as closed loop system. So let's do first for open loop case. So the time domain I could write directly yt is equals to 60 1 minus e to the power minus t1 by 20. I'm just considering time as t1. Okay, so this is a straightforward to write for expression. Now my output is 90% of steady state value, which is 60. So I want to find out the time. So let me call it t1 at which this occur. So I have an equation here. There is one unknown. I can easily compute t1 to be 46 seconds. Now let's see what happened in closed loop case. So in closed loop case, now let me just write vs is equals to k1 by k1k tau s plus 1 k1k. Okay, so this is my transfer function and this is multiplied by rs. So I just do some manipulation and computation. So in case my rs in for closed loop, it's come from here what I have computed earlier. It was like r was 60 0.8 and over here it was r was 0.8. Okay, kilometer per hour. So just be careful for that. Now I just write down the final expression. Vt equals to, I will skip the big bit of computation. So what I have is 61 minus e to the power minus t2 by 0.263, and I just do nothing. I just substitute these value and then compute the inverse Laplace transform, and we by now you know how to do these things. Okay, so about 90% could be 54 again, and then I will compute the value of t2 actually turned out to be just 0.6 seconds. So this is open loop, this is closed loop, and you have seen it's a 77 times approximately faster, right? So if I just have a closed loop, my steady state error is much smaller. Okay, and also my response is pretty fast. So this will motivate us towards analyzing what are the effect of feedback on the system. So first we saw, well, it's happened in steady state response, it's also happened in transient. Okay, so is there any anything else associated with feedback? Now in initial block, we mentioned few other things in addition to reference and output. One was disturbance input and the another was noise input. Okay, so in presence of disturbance and noise, I can compute the overall output of system or the system as sum of response. Just to compute the response by setting RS, and here I am considering DS and NS equals to 0. Then I compute response by disturbance by setting RS and NS equals to 0. And lastly, for noise, I set remaining two inputs to 0 and I just use the superposition. So this is total response to the reference signal, to the disturbance, to the noise. So let us define the loop gain. Loop gain is GS into GS. So if you have remembered from the diagram, my forward loop was GC into G, and this is the controller and this is my plant. Okay, now for the error, of course a function of what is the reference, something to do with controller transfer function and plant transfer function. Similarly disturbance, also noise. So I can just compute directly, and these are the things I think we will discuss how to compute the effect of disturbance in numericals, and then take the total response of system as sum of response to the disturbances and combine it to the response of input, right? Just the superposition. Okay, so when we start the lecture, we said, well, there could be some parameter variation, right? And then how we will see what is the effect of parameter variation on the system. So assume there is no disturbance or noise. Well, we will come to this very shortly. So say my transfer function of plant change from G to delta GS, and then the error signal change accordingly. So I'm not just doing something, I'm just doing something simple here. So ES, as I know, ES is 1 plus LS RS. Okay, and L is equals to GC and G, and G I know now, I am making it GS plus delta GS. So this is how my error will look like. Okay, so this is my error by putting all these in this equation. Okay, now the change in tracking error can be computed. You can just say what is delta ES. So you just take this guy ES, okay, you just take this guy ES on the another side, on this side, okay, and then put the values. ES is 1 by 1 plus LS RS. Then I will get this expression, right? So this says if again delta G is 0, then this goes off. Okay, this is also I am having over here is delta GS is the term. Okay, so that is the vital case to check this. Okay, the change in tracking error is something like this: GCS, delta GS, and you have lots of term of delta GS influencing the particular number. Okay, so if I just take an open loop, right, if I just take an open loop, if you remember, for convenience, if I will draw it here. I'm having GC, I'm having G, then my output is CS, my input is RS. Okay, now the error is usually, error will be RS minus CS. Okay, and in this case this is R. So I will just omit the S for a moment. So C is GC GR, okay, and this is R minus, so E plus delta E is equals to R one minus GC G plus delta G, okay. So delta E, so this is again an open loop, so delta E is equals to minus GC S. I'm just putting this E and then bringing it here. When you compute, you will get this value. So this is again an open loop. Let us compare what will happen in closed loop. So we derived this for closed loop in last slide. I have an error signal, of course, okay. So I do some approximation that GC and into G is much larger than very small change, and I can get an approximate expression like that. So this is change in error, delta E equals to GCS delta G by 1 plus LS square RS, okay. So if you compare this with, you see that the tracking error is reduced by a factor 1 plus LS. I will just erase the pin, okay. So my tracking error is reduced by 1 plus LS. Square or the square, and for large value of L I can just again ignore this one. I can ignore this one, okay, and just write LS. So delta E is equals to minus GC delta G. One is LS, another is also LS, and LS is GC into G, and it will get cancelled, and I will get this expression over here, okay. So this is not difficult to obtain, right? So what does this means? That the larger value of LS result in smaller change in tracking error, okay. Is there something which I could change in LS? Well, LS is, if you just recall, was GC G. So there could be, well, you now change the plant, but I really don't want to do that, right? Because the plant is already I have. There is something which I am giving to control, and I just can't change the subject or the plant. So I can just manipulate my GC. So in such a way that it result in smaller change in tracking error. So this is about how feedback change the error, or how helps in reduction in error. So now what we saw was essentially this delta E relates to small change in system parameter. Now try to quantify that a little more, right? So we call the system sensitivity. So well, we define this one term as ratio of change in transfer function to change in progress transfer, or some small parameters. So I have T as my transfer function. So let's just understand from here. So I want to check how my overall transfer function change with small change in G. So this is what I call as sensitivity change, this S. how does it, how sensitivity in is the transfer function to change in G. Okay, so GSGT, sensitivity of closed loop system. SGT is the sensitivity in transfer function due to change in G. So T here, this is closed loop transfer function. Okay, I'm working with closed loop transfer function. I'm differentiating it with respect to G, and then I'm putting G by T. Okay, when I'm just calculating it, I will get this value. Okay, so how it's look like, sensitivity of my transfer function with respect to G or change in G is simply 1 by 1 plus GCG. Okay, so here we are just finding sensitivity in transfer function with respect to my gain or progress transfer function. And just start with, I'm just looking at sensitivity with respect to disturbance, right? So in which case I set reference and noise to be 0, and I compute the tracking error, right? In so this is ES equals to minus GS 1 plus LS DS. So if you were just to write sensitivity in terms of LS, in last you write sensitivity in terms of L, so it will be 1 plus 1 L, because L is nothing else GCG. Okay, so I'm just writing it in terms of L. So this is my error with respect to disturbance, and I take in this term, right? So 1 by 1 plus LS is my sensitivity of transfer function with change in gain. Okay, then GS and DS, right? So if GS is fixed, which is usually the case, then with increase in loop gain, so I want to reduce the error, right? So typically my error should be 0, and if there is disturbances, there should be no error. Okay, so how do I will, but then if I have a disturbance, I should expect that there is some error. So if there is some error, I would want to minimize the error, right? So GS is fixed, then with increase in loop gain, okay, this guy will get affected, of the disturbance can decrease, right? So something which I will briefly introduce now is, okay, so A is something related to frequency. We will talk a little more of this when we talk about frequency domain. So disturbance signals are typically signals of low frequency, right? So it may be like step, or even if there is oscillatory behavior, or in the disturbance, they will just be at very low frequency. In the car example, my disturbance are either I hit uphill or downhill or something, like it will just be constant thing without any disturbance, right? So disturbance signals are mostly introduced, or they usually occurs at low frequency. Okay, so my LS is okay. If I look at how it vary with frequency, I can just see the magnitude of L, J, omega at frequency, right? So at low frequency, so what does it say? That this expression tell me that with increase in loop gain, the effect of disturbance decreases. Now I do not have to increase it like forever, right? So LS I know depends on frequency, and my disturbances signals are associated with certain frequency or certain low frequency. So I want this LS to increase at low frequency. This should be big at low frequency. So this is essentially mean that I increase the controller gain, okay, at low frequency, or in another word, I am just, so if I increase my sensitivity will decrease, okay. So I ideally I don't want to be sensitivity or disturbance, right? So whatever happens I just should reject it. So but typically to increase this at low frequency my sensitivity decreases, right? At low frequency I don't really care what happen at high frequency at the moment, because there is no disturbance signals which comes at high frequency, okay. Now what about the noise, right? We so far have not talked about it, but then usually my measurement comes with some noise, right? So tracking in terms of measurements is something error in terms of measurement is something like this, right? Again from the original expression which is obtained, that is LS by is known as complementary sensitivity function. So some people denote it as T, some people denote it as C, okay. And since we have already used T and C, we will just say this may be just S dash, okay, the complementary sensitivity function, okay. Then this noise or small loop gain, if this is LS is very small, it's led to a good noise attenuation, right? Because the effect of noise would be reduced, and typically noise signals are signals which occur at very high frequency or which get into system. These signals are typically high frequency signal. So for purpose of noise attenuation, the loop is turned to be of low value at very high frequency, right? Previously what we had, that I want loop gain to higher at low frequency, that will eliminate my disturbance. For the purpose of noise attenuation, the loop gain is turned to have lower value at high frequency, right? So when I do this, the controller gain is increased at low frequency for disturbance rejection and decrease at higher frequency for noise attenuation, right? So it's like some kind of complementary effect over here. So these are two ways which you know based on what is L. I can ideally deal with disturbance and noise together, or reduce the effect of disturbance and effect of measurement noise. So we will do more of this when we do frequency response, like what is actually mean, what is low frequency, what is high frequency, and so on, and how do I actually go about computing these things. That's we will keep till a little later when we do frequency response analysis, okay. And then something which we will use throughout for now on is what is called as characteristic equation, right? So what is characteristic equation? Well, it is just a transfer function, and I'll look at what is its denominator. So I know how to compute, right? GS in the forward gain is the forward gain, HS is the negative loop, the overall transfer function TS is GS 1 plus GSHS. It is basically TS from RS to, this is RS to CS. This is my reference signal, okay. So TS is G by 1 plus GSHS, okay. So the characteristic equation is when I equate the denominator of this guy to equals to 0, right? So 1 plus gs hs equals to 0, and if hs is equals to 1, then I'm kind of something very simple, right? Like 1 plus gs is equals to 0. Okay, so now if I assume the system with non-unity feedback, now the assumed system was non-unity feedback system. Now is it possible that I do some magic and I convert this to a system which look like, let me call this as g dash s, and then a plus sign, a minus, and this is unity, this is rs, okay, and this guy is cs, right? So I just want to convert non-unity system to a unity system, unity feedback system. Can I do this? The answer is yes. So what I do, I just compute or evaluate how will the transfer function look like. Okay, so that will be g dash 1 plus g dash s, and then I find out what is g dash in terms of gs and 1 plus gs hs. This is when I am having non-unity feedback, this is when I am having unity feedback. So in terms of gs and hs, I will find out g dash h. So non-unity feedback system can transform into unity by just using this transformation. This should be very straightforward to compute because we are just dealing with very easy looking linear equation over here. Okay, so g dash s would be gs by 1 minus gs plus gs hs. Okay, g h dash s is equals to 1, right? So while I do this, the characterized equation remains the same, characteristics equation will remains the same. So if I just look at, it is 1 plus g dash h dash s. So this is 1 plus g dash s is equals to 1 plus gs hs, right? So this is nothing special happening over here. Yeah, so let's revisit stability for a while. So I start with the system that look like this. Okay, so I know that this is unstable because there is one loop, one pole on right hand plane. This is the pole which is on right hand plane. Okay, so anything on right hand side unstable, right? So can I do something with this, right? Can I do something as to make the system stable? Well, I just say I just take negative feedback, hs is equals to 3, and I take the closed loop transfer function, set the characteristics equation is equals to 0, and the pole of closed loop systems are now minus 1 by 2 plus minus j under root 3 by 2, right? So these are complex conjugate poles, but which are again in LHS, right? So in LHS left half plane, right? So this guy, all the poles are to the left half plane, therefore the closed loop system is stable, right? So I start with open loop system which is unstable. I can stabilize it with just some feedback, right? So this is one advantage which I get when I do feedback, right? I can make unstable system stable. Is it possible always that give me any unstable system, and can I make it stable by feedback? Well, that may not be always possible, but in several cases it is possible. So what are the advantages? The advantages are, I can see that I can have improved stability, I can deal with noise, right? And we could also increase bandwidth. We will see this when we do frequency response of the system. But then my overall gain of the system reduced, right? Because I have some multiplication factor over there, and so I go and kind of give you some attenuation which may not always be desirable. So that's one of the drawback. Of course, I could have increased the cost to deal cost and sometimes a bit of complexity too. But of course, the advantage are a lot more compared to disadvantage. So let's revisit stability for a while. So I start with the system that looks like this. Okay, so I know that this is unstable because there is one loop, one pole on right hand plane. This is the pole which is on right hand plane. Okay, so anything on right hand side unstable, right? So can I do something with this, right? Can I do something as to make the system stable? Well, I just take negative feedback hs is equals to 3, and I take the closed loop transfer function, set the characteristics equation is equals to 0, and the pole of closed loop systems are now minus 1 by 2 plus minus j under root 3 by 2, right? So these are complex conjugate poles, but which are again in LHS, right? So in LHS left half plane, right? So this guy, all the poles are to the left half plane, therefore the closed loop system is stable, right? So I start with open loop system which is unstable. I can stabilize it with just some feedback, right? So this is one advantage which I get when I do feedback, right? I can make unstable system stable. Is it possible always that give me any unstable system, and can I make it stable by feedback? Well, that may not be always possible, but in several cases it is possible. So what are the advantages? The advantages are, I can see that I can have improved stability, I can deal with noise, right? And we could also increase bandwidth. We will see this when we do frequency response of the system. But then my overall gain of the system reduced, right? Because I have some multiplication factor over there, and so I go and kind of give you some attenuation which may not always be desirable. So that's one of the drawback. Of course, I could have increased the cost to deal cost and sometimes a bit of complexity too. But of course, the advantage are a lot more compared to disadvantage. So sometime now we have seen how the system should be sensitivity to change in parameters, right? So we will see, does that have any effect on stability? That is called as relative stability. So sometime we have seen the how the system could be sensitive to change in parameter, right? So we will see, does that have an effect on stability, and that is called relative stability. So at a moment we just talk about, is the system stable or unstable, right? Nothing more. So how given a system can be defined as some kind of relative stability? Relative stability means a small change in parameter of the system make it unstable, right? Then that will define it as, well, there will be also some kind of measure of stability, that if my system parameters are between so and so, I could still be stable, right? For example, if I'm cooking food and I just download something from khana.com, and all those website I say, they say 1 tablespoon of salt, But if I just put one table and plus 1% or minus 1%, it does not really kill the taste, right? But if I put 2 tablespoons, that might be awful. If I put 0 tablespoon, that may still not be very good. So, but then there is some amount of relative stability, right? You can go slightly higher, slightly lower, and still maintain stability, right? Stability in terms of taste. But if I'm making tandoori chicken and it says put on oven for 20 minutes, but if I say 22 minutes, then I might, not really get something very edible, right? So that's the little thing could be unstable over here. Okay, 20 minutes 1 second could be okay, but if I do 20 minutes to plus 2 or more minutes, that could, give me something very strange, right? So these are the things which, change in little parameters sometime affect stability, could affect stability. So if I'm looking at, I know I am playing a cricket match, my team is chasing a score for something, some 20 overs, and at the end of 15 over I'm still need 40 runs with 5 wickets in hand. I could still say I can still win the game, right? Because my required rate is not too much, but all of a sudden if I lose 2 wickets, right, then that would be recipe of disaster. I could go from a winning zone directly to a losing zone, right? So these are the things where you are stable, you can all of a sudden unstable, and that is exactly what is the concept of relative stability. So we don't really deals with food or sports here, we deals with physical system. So what is deal means in our case, right? So we look at our stability in terms of location of poles, right? So well, typical complex or real poles or whatever, right? So what I said in terms of system, if I say, well, I am here, so there are my poles, and I have a system which typically could look like K, G, H, here it is, plus, minus, R, C, the output. And I had designed my system. I work very hard. I say, well, my system is stable, it has poles at minus 0.1. Okay, so I give a fascinating design problem, and I just say this, my poles are at um, 0.1 plus minus j, somewhat 2j, and I work very hard. I substitute this as my thesis, and I say my controller works because my poles are here, right? So these are my poles. The 2 days later, my supervisor come and check it. Something could have gone wrong. They're right. My mass would have been a little different than earlier. Some rats might have chewed on or something where my mass slightly decrease, and when I run the system again, maybe and these guys just jump here, right? Or maybe I did it air conditioner environment, the power goes off, and I'm representing this examiner or my supervisor in different environment where the parameter might change and say, oh, what I see the response, so it's go unstable, right? So my poles could just be, instead of minus 0.1, just become positive. This could happen, right? So well, see, there are lots of cases where this happens, and when I design things, I will see, well, I don't want stability, I just think like more stable, right? So it is like right somewhere. So I want my poles to be somewhere here, just left of 0, but say minus 1,